Okay, in this video, I would like to continue talking about the differences between confined and unconfined aquifer. And what I'm going to do, I'm going to try to answer some of questions that I believe you have. If you remember last session, we talked about the 3D models, 2D models, and 1D models in both confined and unconfined systems. And if you remember, we said that the unconfined systems are inherently 2D or 1D problems. Okay, and we said that actually it is 2D mainly because we already to be able to handle the unconfined flows, we already assumed that the system is the water flows parallelly like this, and we don't have any vertical components in the unconfined aquifer. So technically it is a depth average problem. Okay, so that's why we technically we say that actually unconfined aquifers are technically 2D problems. Okay, but there are a few things that I would like to talk about. So the first thing is that technically, if you want, so the problem with the unconfined aquifer is that we already talked about that, is that actually the thickness of aquifer is now just it is not constant, and actually it is h. And technically, if you want to find the flow rate, so technically you need to multiply, so technically your q is q star times h, right? So but I want you to think about, but the other problem here in the unconfined aquifer is that, so for if you look at the confined system, in the unconfined system, you can say that these two layers are confining the aquifer, and this is one physical boundary, and this is the other physical boundary. Okay, but here we have a physical boundary here, but technically we cannot define a physical boundary on the groundwater table. Okay, so but what we technically in this soil physics people or scientists do is that technically they go and consider this area, the surface of the ground, technically as a boundary, physical boundary, or even, okay, so what happens here, so they assume that if rainfall happens here, now they consider that actually how the water gets into the system and how it will impact the groundwater level table, and how the groundwater level table would change. So this is one way people look at the unconfined system. Technically, soil physics scientists are looking at this problem, and this is nothing but a recharge. Okay. The other things that I would like to talk about is that, is there any way we consider a 3D flow within an unconfined aquifer or not? Okay, so this is a very valid question. So technically, we said that the unconfined aquifers are technically 2D groundwater problems, and the reason for saying that was everything was related to the Dupuit's assumptions, right? But using the advanced mod flow software, there are packages that actually are known as layer packages. Okay, so these layer packages allow us to define each numerical layer. So if this if this is my confined aquifer, unconfined aquifer, and if I want to discretize this system and use cells, for example, I would model my unconfined aquifer like these. So these yellow spaces are my numerical nodes or numerical cells. Okay, so okay, so I can define boundary condition 1 here and boundary condition 2 here, and actually write the governing equation here and solve this problem. And for example, if the boundary condition 1 changes, then I can go and calculate how the water profile, the groundwater table would change. But in this system, we said that technically these system is everything here is unconfined. Okay, but if, for example, instead of having one layers, if I had vertically, if I would define vertical layers like this, for example, okay, so in this situation, the mud flow, the layer package that we have in ModFlow led us to consider technically two types of cells. So type 1 is confined cells. Type 2 is, they call it convertible cells. What it means that the software automatically goes and check if the groundwater table is above the top of the cell, then it will consider the cell or layer as a confined aquifer. And the confined governing equation is valid, and it's going to be used in these two cells, two layers, for example. Okay, so it means that actually technically you're going to use the SS or S parameters. And another important thing is that the entire flow, so the entire face of each cells are contributing into the flux exchange. Okay, but if the groundwater table is below the top of the layer like this, it will consider this as an unconfined aquifer, and all the unconfined groundwater equation is valid there, which is a 2D, and then it will use SY storage coefficients. And it is very important that now the model will go and consider this phase, the saturated phase, as the phase which is associated with the flux changes. So saying that, I want to clarify this, that the advanced ModFlow models can technically consider or takes care of the unsaturated, unconfined aquifers using multiple layers, and also considering and defining those layers as convertible cells. Okay, but remember that actually in this area, which is unconfined, everything is 2D, and for example, the duplex assumption is even much more valid here in this area. Okay, so these were two important things that I wanted to clarify. So the one was the Richard's equations and what they do, or unsaturated groundwater flow, which is a totally different things. And in that case, actually, this is the boundary condition. Okay, and technically we are looking at how the groundwater, actually the rainfall or surface recharge gets into the groundwater table, which itself, so we are not talking about this, but there are some packages that actually they can take care of this type of flows. And the other thing was that was the convertible cells or layers concept. Okay, so to make things more clear, I would like to solve another example problem and see how we can take care of the unconfined groundwater flow problems. So in this problem, my example problem looks like this. So example problem. So in this problem, I have a river like this here. So there is a lake here. Everything goes, and I have ocean. Okay, so this would be my ocean or huge river like Mississippi River. Okay, so here there is a lake or wetland, and this is another river. Okay, and here this is the unconfined layer, sorry, the confining layer, bedrock. The head here is measured as h2 equals 80 meter. Here the bottom of the lake is almost 94 meters, so this is a shallow wetland. And from the water table, for example, to the bedrock is 94 meter, and this is the river, which its stage is measured as h1 equals 100 meter. K is 0.6 meter per day, and the distance from the stream to the lake is 100 meter, and from the measuring point to the ocean is 300 meter. Okay, so there are so many interesting questions that actually we would like to answer. Okay, for example, question A is, what is the N required to keep the wetland wet? So technically, what happened here? So let me, so okay, so if this is my wetland, technically I want to make sure that we have enough N that this wetland will be remained wet. So now here N is unknown, that actually we would like to go and find. Question B is final h max between river and lake, C find x max between river and lake, and what is water level below the wetland if n is 0. Okay, so these are the example questions that we have. Let me fix this. So the k value is actually 0.5. Okay, and in this specific problem, we assume that the system is in the steady state condition, and we can write the governing equation for this specific problem as k h partial x plus n equals sy partial h partial t, which itself is 0 because we are assuming that the system is in the steady state condition. And if the kx is constant within the system, technically we can go and take even k out of the system. So knowing the fact that the first derivative of h squared is 2h partial x. So using this, let's say mathematical formula or calculus formula, so we went and applied this formula. You can go and watch the previous videos that I shared with you. So using this and putting it there, technically I would go and convert. So if I combine these two, technically I can go and write this equation. Okay, so I don't want to repeat everything again because you have the video and you can go and watch. And I remember I solved one example problem, how we can apply this calculus formula into this and technically take care of this and convert everything or convert this equation into this form of equation. Okay, so if I integrate once from this equation, then I can write d of h squared dx is negative 2n kx plus c1. And if I integrate again, I can write h2 equals negative 2, negative n so let me write it down. This will be negative 2 n x squared 2k, right, plus c1x plus c2, which is n k x squared plus c1x plus c2. Okay, now let's see what are my boundary conditions. What are the so technically the unknowns that I have in this problem is C1, C2, and N. Okay, I have three unknowns. And let's see what are the known boundary conditions for me. So at x equals 0, I know that the h0 is 100 meter. So this is the stream. Okay, so this is the head in the left stream. At x equal L, which actually at x equals 1000 meter. So technically at h 1000, the head is 80 meter. Okay, so this is the head at the ocean, and also at x equal 700 meter for I assume that the wetland water table is at 94 meters. So I have three unknowns and three known boundary conditions. Technically, I should be able to go solve this problem. Okay, in question A, we wanted to know what would be the required N recharge value to keep the groundwater level high enough to keep the wetland wet. So we assume that actually we want to have, if this was our wetland, we want to have at least the water table, groundwater table be at 94 meter. Okay, and now we are interested to know that actually what would be the required N value here. Okay, so to solve that problem, this is the, let me copy. Oops. Okay, so this is the H squared. This is the analytical solutions that I have. If I apply this boundary condition into this equation, technically if I substitute x with 0, technically h square at 0 equals 0 plus 0 plus c2. This says that at h0 it is 100, so 10,000 will be my c2. Okay, and if I go and apply okay, so now c2, I have the value for c2. Okay, so the c2 is 10,000. Now if I use the second boundary condition at the ocean, I would say that at h 1000 everything raised to the power of 2 negative nk 10,000 square plus c1 10,000 plus 10,000, then this equals with 80 square. Okay, so this can be, so I will name this as equation 1 that I have, because if you look at this equation, there are two unknowns here. So N is unknown and C is unknown. So two unknowns here, and solve this, I need to have two equations. So this is equation 1, and for equation 2, I can use the wetland boundary condition, and technically I will apply this boundary condition. Okay, so similarly, I will go and write at each 100 meter raised to the power of 2, and by the way, the value of the value of k is known, right? So let me write it as 0.5 or whatever it was. So at 0.5, 700 square plus 700 C1 plus 10,000, and this is another. This is my equation 2. So I'm not going to solve this problem because this is actually one of your homework problems that I want you yourself go and write it again you yourself and practice it. So, but technically here I have two equations, two unknowns, and I should be able to go and find the value of n and the value of C1. Okay, both at a time. So if I have that similarly, I can go and solve, let's see what were the other problems. So now I have that equation. So to solve B, to find H max and X max between the river and the lake here, I can go, if I have, now I have NC1, C2. So technically I have the H X square function. Okay, so which is a function of x and k, or let me don't make it complex. So I have the x2 square function, whatever it is, in the cloud. So technically now I need just to go and find or solve this equation, okay, to 0. So if I solve this equation, if I solve for x, I will be able to go and find x max, and similarly if I plug in x max here, I should be able to find h max. Then it means that actually I can find the groundwater divide position. Okay, so having that, then I can go and solve for qx, which is negative k h delta h delta x at any x that I am interested in. Okay, so this is, I can go and solve these two questions like that. And the last question was that what is the water level between the wetland if n is 0? So if n is 0, so technically if n is 0, if you go and write the governing equation from the beginning like this, so this is already considered as, so this is given, n is 0. So technically what you need to go and you have two boundary conditions. So think about this problem. So now you have only two boundary conditions, and you need to go and solve, simply you can go and solve this problem. So this is one example problem that I want you to actually talk about it a little bit. And I think that's enough. So in this session, I just wanted to clarify and talk more about the unconfined aquifer. Unfortunately, because of this COVID-19 unprecedented situation, we couldn't have any class. But if you have any question, just send me an email, and I will try do my best to answer your questions. But next session, I'm going to go and talk about the radial flow governing equation, which is this is something that actually you definitely need to know if you want to be a groundwater modeler, and we'll move on from that session.